Righto, so in this screencast we're going to look at geometric series and something known as convergent or infinite sums or series. A special case of geometric series. Alright, so what have we done so far? We've looked at, this is the fourth YouTube in this section in chapter 6, and we've looked at, for an arithmetic, we've looked at the nth term. For geometric, we've looked at the nth term. We've looked at the nth, the sum to n terms of an arithmetic. So now we're going to look at the sum to n terms for a geometric series, and that is, now I'm going to just go straight into it. There is a nice little proof. It's quite a straightforward one. It's on page 175 if you want to look over it. But we're going to get straight into the formula again. I remind you that this is available to you on your formula sheet when you sit a paper, when you sit an exam. So this will give you the sum to n terms of a geometric series. This is our first term, this is our common ratio, it's the number of terms. And sometimes it's to avoid having a negative denominator. This is the preferable version, but they're both the same, they both get you the result. So what we're going to do is, I'm just going to look at some examples of how to calculate these series, and then we'll look at convergent series, and then we'll close this lesson. Okay, let's have a look at this example here. Calculate the sum of the first 12 terms of the series 1 plus 3 plus 9, ... obviously going on to the first 12 terms. Right, what do we need? Well, we need to know the sum of 12 terms. We're going to need the first term. Now we're going to use r to the n minus 1 over r minus 1, because r in this case we can calculate any term divided by the term in front is equal to 3. That works for 9 divided by 3 and 3 divided by 1. We know that u1 is equal to our first term there, 1, and n is equal to 12. So with that information we can launch into finding the sum. So u1 is 1, r is 3, n is 12, and we use the r minus 1 rather than 1 minus r formula, because r is positive, it's greater than 1. If it's less than 1, it's useful to use the other one. 3 minus 1 goes underneath, so it's a 2. So we've got a half by 3 to the 12 minus 1. Nip over here to the calculator. So it'll be a half by 3 to the power of 12, get out of the power, minus 1, and hit enter. 265,720 is 265,720 is our result. That's our sum there of the first 12 terms. You see, with geometrics, much larger numbers, so the use of the calculator, and therefore these questions are more likely to appear in paper 2. Okay, next example. Okay, second example is here in front of us. Find the number of terms in the sequence 8192 plus 6144 plus 4608. What do we got here when we do this division? What is our, I'm figuring it's going to be geometric, what is our common ratio? So 6144 divided by 8192, 6144 over 8192. Let's have a look at that. 6144 over 8192. 6144 over 8192. This will give us 3/4. So that there is equal to 3/4. Let's just check that 4608 over 6144 is the same for 4608. 4608, and over 6144, and that's also 3/4. So we have a geometric, so that's also r equals 3/4. So our r is 3/4. We have a u1 of 8192. We have an SN, a TN, a UN of 1458, and we want to know what n is. How many terms? What is this? What term is this? So we're going to use the nth term formula to determine this. So 1458 is equal to u1, 8192, times r 3/4 to the power of n minus 1. I don't know what n is. So let's work this out. This is going to be 3/4 to the power of n minus 1, which equals 1458 over 8192. 1458 over 8192. Let's see if we can bring that down. 1458 over 8192. That just goes back to 729 over 4096. 729, 4096. So what we need to do is work out the power that you take 3/4 to get this value here. That's just going to be trial and error. Now later on in this course we're going to learn a bit about logarithms, a lot actually, and we're going to be able to use it to solve such equations. However, at this section of the course, I'm guessing that we haven't done logarithms yet, and so although I'm just looking back in the textbook now, it does appear in chapter 4, so they are assuming some logarithms knowledge, but we haven't studied it yet. So what we're going to do is, I know that n is going to have to be a whole number, so I can get 3/4 to a positive integer to be 729 over 4096, and that will be and then I'll be able to figure out what n is from that. So that'll just be from trial and error. 3/4 to different powers to get this. Now I'm thinking, really, I want to know 3 to the power of what gives me 729. That's my clue. So 3 to the power of, what are we going to say, 7 is too many. 3 to the power of 6 maybe gives me 729. Yep, it does. So, and 4 to the power of 6. So I'm guessing that 3/4 to the power of 6 will equal, so we'll check with 4 to the power of 6. 4 to the power of 6 is 4096. So you know that when you take a fraction to a power, you can split the numerator and denominator to that power. So 3 to the 6 over 4 to the 6. That's equal to 729 over 4096. So therefore, n is equal to 7. So there are 7 terms in this sequence. That there is equal to u7. Calculate the sum of the terms. So we're now after the sum of these 7 terms, which is, now because r is equal to 3/4, I'd rather use the 1 minus r rather than r minus 1. So I'm going to go u1, 1 minus r to the n over 1 minus r. So u1 being 8192, r being 3/4, and n equaling 7, all over 1 minus r being 3/4, so that's 1/4. So we'll work that out. Okay, I've just popped that calculation into the calculator. 8192, 28394 is the result. So the sum is 28,394. Okay, just want to have a look now at convergent sums. This concept of sums that can converge on a value, or sometimes called sums to infinity. Okay, if we just pick out any old, right, so the old 1 plus 3 plus 9 plus 27, and we have a look at this. Now this sum is obviously getting larger and larger and larger, isn't it? And if we took even 10 terms, it's an enormous sum. 20 or 100 terms, huge. But it's not converging, it's just getting bigger and bigger and bigger. Now think about, so we couldn't really take an infinite sum of this. It just gets too large. But what we want to do is, perhaps I just want to have a little explore of a geometric sum where the terms get smaller. So if we start with, say, 4 and add 2 and then 1, and right, so our ratio here is a half. What we're finding here is, as we keep going and get smaller and smaller, is that these terms pretty soon become very, very small. 1 over 512, 1 over 1024 gets small. So what we can do here is have a look at this sum and notice that it's converging here on on a value. So let's just take it bit by bit. 4 plus 2, that gives us 6, plus 1 is 7. Now it's 7.5. Now it's 7 3/4. Now it's 7 and, what's that, 7/8. Now it's 7 and 15/16. And what we're going to find is that we're just always short of 8. But we're getting closer to 8. 63/64 there. This is 7 and 127. You get the idea. 128. This one here, boom, boom, boom. This one here, all the way to there is 7. So we're adding up all these terms here. 7 and 1023/1024. So you get the idea. And what we're doing is looking here at a sum that converges on a figure. Now that figure, we can, it's getting closer to 8, isn't it? So we can say it's converging on 8. Never actually reaches 8, but the sum to infinity, we say that the sum to infinity, which is written like so, is equal to, in this case, 8, because it is getting so close to 8. It's asymptotic, never quite going to reach it, but that's what it's converging on. And sometimes we talk about in maths things getting closer, limiting values. That's what we're looking at here. So, okay, how to calculate it? Well, we go back to our sum to n terms, all right, of u1 1 minus r to the n over 1 minus r. Okay, now let's think about this sum, but for values of r. Let's think about the values of r that make our terms get smaller, so that we might have a convergent sum. We looked up here where r is equal to 3, gets bigger. So if we're doubling each time, anything greater than 1 or less than minus 1, our terms are getting bigger. And so therefore, the values of r between minus 1, not including, but between minus 1 and 1, for those values there of r, what we're getting are smaller and smaller and ever smaller terms, to the point where they become so small that we're getting very close very quickly to a figure, and we're converging on it. So for these values of r, very important point, for these values of r for our common ratio, the geometric series will converge. Converge is that word there that I haven't written very neatly. Will converge on a figure. Will converge for these values of r. Okay, so let's think about this. Let's then look at what is happening. So Sn is equal to, let's say n is equal to infinity. All right, we're looking at an infinite number of terms. N is equal to infinity. Okay, so now we're looking for the sum to infinity of our sequence. U1 is obviously unchanged, but 1 minus r to the power of infinity. Oh, that's pretty crazy. Let's come back to that 1 minus r. This 1 minus r to the infinity. Remember, r is between minus 1 and 1, so it's a fraction. It's a half. It's a third. It's a quarter. If you take a quarter and raise it to a huge number, all right, let's just play around with this. 0.25. I know, put it to 100. That's crazy. Look at this. Now this says 6.2 times 10 to the minus. This here means minus 61. That means move this decimal point 61 places to the left. So you're going to have 0.000, 65 zeros, 62. That is ridiculously small. That is immensely small. So what we've got there is, that's just power 100. I could have gone 1,000, 10,000. So the point we're making here is that you take a fraction to a large power, it's going to zero. That is as good as 0, isn't it? That is so close to 0, it's not funny. It's such a small figure. So we actually are going to say that, here that for for n between for r between minus 1 and 1, that the sum, for r between minus 1 and 1, r to the power of infinity is equal to 0. Because that's what it's converging on 0. That's the convergence. So for that value, r to the power of infinity equals 0. It's getting closer to 0. It's so close to 0, we're going to rule it out. So we're actually going to, for these values of r, we're going to go like this. And that's equal to 0 now. So if we go back and look at our formula, we rewrite it as s to the power of infinity equals, the infinite sum equals infinite number of terms. That's what this infinite symbol here is representing. 1 minus 0 over 1 minus r. That can be simplified, can't it? To u1 by 1 over 1 minus r. So there is my nice simple convergent series formula. First term over 1 minus r. How nice is that? Let's check it for this sequence here. 4 plus 2 plus 1, we reckon it's 8. Is it right? Let's go back. So for the example above, for the example above, what have we got? We've got r is equal to 1/2 and u1 is equal to 4. Alright, so s infinity equals 4 over 1 minus 1/2, which equals a 4 over 1/2, which equals 8. So we've got 8 there, and that's what we figured. We're getting closer to 8. So that's the convergent sum. That's equal to 8. Let's have a look at one more example. Okay, I think this is a nice example. This is our last one before I close the lesson. For this series, 18 plus 6 plus 2, find S10, S15, S60. Right, so what's happening here? 18 to 6, so we take any term, divide by the term in front. 6 over 18, 1/3. 2 over 6, 1/3. So our ratio is 1/3. Our first term is equal to 18. So what's S10 equal to? Right, S10 is equal to U1, 18. Now we're going to use 1 minus r to the power of 10 over 1 minus r, so that's 2/3. Alright, let's calculate that. And it calculates out to 26.9995. So that's our S10, 26.9995. Now, right, so you can probably see where this is going. Because r is 1/3, it does have a convergent series, and we're gonna look at, we've looked at the sum of the first 10. What do you reckon the sum of the first 15 is going to be? The only change here is now 1 minus 1/3 to the power of 15 over 2/3. We go back into our calculator. We just change our power here to 15. Make that 1/5. Sorry, just try that again. Alright, so I think what we've got to do here is copy this down, don't we? So we just hit that. And now we can go in and change that to 15. And we've got a number, just when I approximate that, 27. That's equal to 27. Now, I don't think it's actually equal to 27. I think the calculator is rounded it off because it is so close to 27. Now, the infinite sum, take a guess at what that's going to be. First term, 18 over 2/3. I don't need a calculator for this. Times top and bottom by 3, 54 over 2, which equals 27. There's our infinite sum. But we were so close to that. We were within 5/10,000ths of it with the first 10 terms. So you go to infinity and you're only just that little bit closer to 27. Okay. Big long screencast. I apologise for the length of this. We can do 6, I think 6J and 6K, if I am not mistaken. I and J are both geometric, and K is convergent. After this, we've just got some applications of series, and then we move into Pascal's triangle. Okay, see you in class.